In the final exercise of yesterday's video, we practiced finding the components of a vector given its magnitude and its direction. We found that the technique for finding the components of a vector in such a situation was very similar to the formulas that were used to convert from polar coordinates to Cartesian coordinates. Today we're going to write down some formulas that can be used to help us define components of a vector in various situations, similar to what we saw in the exercises yesterday. And we're also going to practice going backward, taking the components of a vector and calculating its magnitude and its direction angle. To begin with, let's establish a little bit of terminology and notation. We said yesterday that a vector was an object that communicated both a number and a direction. The number associated with the vector has a specific name, a specific mathematical name. The number communicated by a vector is called the vector's magnitude. This is specifically in reference, I believe, to the fact that if the vector represents a force, then the number communicated by that vector represents the magnitude or the strength of that force. More generally, in mathematics, we call the number communicated by any vector the magnitude of that vector. Now, when we are writing down vectors whose components are not known, it usually is represented by the letters V, U, or W. And to emphasize that these letters are stand-ins for unknown vectors and not unknown numbers, we typically will write a little arrow on top of V and U and W. These are typical letters for unknown vectors. Now, personally, I am not particularly uptight about whether or not you remember to put a vector arrow on top of a vector letter, a letter that's being used to represent a vector. Because in mathematics, we are not particularly careful about making sure that vectors have arrows on them and scalars do not. However, be careful. In physics and engineering, they're very strict about this. I feel that vectors have to be written with an arrow on the top. Now, if you have a vector, which I will just generically call V with an arrow on the top, there's specific notation for the magnitude of that vector. One common notation is to take V and to put vertical bars around it, similar to the absolute value bars. This is how we denote the magnitude of the vector, which is called V, with the vector arrow on top of it. Another way to represent this same quantity that I think is more common in mathematics sometimes is to have two vertical bars around the vector just so that it doesn't look like you're trying to take the absolute value. These vertical bars surrounding a vector quantity are asking for the length of the vector. Now let's go ahead and take a vector with a given magnitude and direction angle, and then figure out what its components would be. So I'm given a vector with a magnitude of 7 units. In other words, the magnitude of the vector in this problem is equal to 7. And the associated direction is described by an angle of 30 degrees. Let's write down the vector in component form. Yesterday we saw that if we drew this arrow with its tail at the origin, 7 units long with an angle of 30 degrees, then the position of the arrowhead was exactly the same as the location described in polar coordinates by r equals 7 and theta equals 30 degrees. So finding the components, the horizontal and vertical components of this vector, was equivalent to finding the location of the arrowhead in Cartesian coordinates, x and y. So to find the horizontal component, we can take the magnitude of 7 and take cosine of the angle 30. To find the vertical component, the y component, we can take 7 and multiply it by sine of the angle 30. So cosine of 30 degrees is root 3 over 2. Sine of 30 degrees is 1/2. This would be the horizontal and vertical components of the vector drawn here in blue. In general, if we want to find the components of a vector with a magnitude of r and a direction angle theta, then that can be found using the formula that x component is r multiplied by cosine of your direction angle, and the y component is r multiplied by sine of your direction angle. Exactly the same formulas that we saw when we were converting polar to rectangular. Now, converting from magnitude and direction into components was functionally equivalent to converting from polar into Cartesian coordinate systems. Now imagine that we're going backward. Suppose that we're given a vector in components and we want to calculate the magnitude and the direction. As you might be able to imagine, the formulas for going backward are the same as the formulas for taking a Cartesian point and figuring out what it would be in polar coordinates. For example, someone says to me, let's draw the vector 2, 5. So I'll draw it in the traditional way, with its tail at 0, 0, and the arrowhead at the point 2, 5. They say, what is the magnitude and what is the direction angle? Well, the magnitude, the length of this arrow, is going to be the same as the distance between the origin and this point 2, 5. So the distance from the origin to the point 2, 5 satisfies the equation that the distance squared is equal to the x squared plus the y squared. So r squared is equal to 4 plus 25, 29, and therefore r itself would equal to positive 29. That would be the magnitude. To find the angle, I would first note that the arrowhead of this vector is located in quadrant number 1. So I could find this angle by taking inverse tangent of the y component, 5, divided by the x component. So this would be equal to approximately 68.2 degrees. That would be the direction angle corresponding to this vector. More generally, if we wanted to find the magnitude r and the direction angle theta for a vector whose components were equal to a and b, then the magnitude can be found by taking a squared, the x component, plus b squared, the y component, and then r squared would be equal to the sum of those quantities. Meanwhile, the formula for theta would be different depending on the quadrant into which the vector pointed. If you had a point that was located in either quadrant 1 or quadrant 4, you could find the angle simply by taking inverse tangent of the y component divided by the x component. If the arrowhead was located in quadrants 2 or quadrants 3, then arctan by itself would not be able to produce the correct angle, and you would need to add a half rotation. And just like we saw with polar coordinates, theta must be found manually if the x is equal to 0. The x component being called a in this particular setting. Let's apply these formulas in an exercise. So for the first example, suppose we have a person who is walking in a direction which is 30 degrees south of east. So using the standard convention that north is up and east is to the right, 30 degrees south of east would be hereabouts. The angle corresponding to this movement would be negative 30 degrees. You can turn clockwise by 30 degrees from the positive x-axis to reach this direction. Now we are also told that the person's speed is 5 kilometers per hour. So to represent the person's velocity, I could draw a vector with a length of 5, the length of the vector being the speed of this person's movement. From this data, let's find a vector and let's write it down symbolically in component form. To represent the velocity, all I have to do is use the formula that gives me the components of a vector given its magnitude and its angle. The components of this velocity vector are equal to 5 times cosine of negative 30 degrees, 5 times sine of negative 30 degrees, and based on our reference circle, this would be equal to 5 times square root 3 over 2, negative 5, divided by 2. In this case, we are told that the magnitude of gravitational force is equal to the acceleration due to gravity, which is 9.8, multiplied by an object's mass. The direction of the force is straight down toward the center of the Earth. Hold on, there are a bunch of typos in this paragraph and they're bothering me. Okay, I don't know where I was at when I typed that paragraph, but I was clearly not in a very good place. Having fixed the typos, let's go ahead and answer the question. Let's find a vector, specifically one that is described symbolically using components, which represents the gravitational force that is applied to an object with a mass of 10 kilograms. Okay, so the magnitude of gravitational force, we are told, is equal to 9.8 times the object's mass. This is a specific formula for the gravitational force applied by Earth to an object. So the mass of the object was 10 kilograms, and if I multiply that by 9.8, I get a magnitude of 98 units. Now they tell me that the direction is straight down. So there are a couple of different ways that I could approach this problem. One would be to graph this vector and to note that the vector pointing straight down with a length of 98 units, the arrowhead will be located at the point 0, negative 98. And from that I can determine the components of the vector. The vector stretches from 0, 0 to the location 0, negative 98. This would be the vector representing the gravitational force applied to a 10 kilogram object. Now let's also look at the case where we have a vector which is stretching between one given point and another given point. For example, in the first exercise, we have a vector and we're told that it stretches from the point a equals negative 1, 3 to the point 2, 0. Draw the vector and then find its components. So this is quite similar to one of the exercises from yesterday. Our vector stretches from one point on the xy plane, -1, 3, to another point on the xy plane, 2, 0. Our goal is to find the components of this vector, which amounts to figuring out what would happen to the arrowhead if this same vector was drawn starting from the origin. Now, to recreate this vector as drawn from the origin, I'm going to think about what it takes in terms of horizontal and vertical movement to get from point A to point B. Horizontally, I'd have to move 3 units to the right, and vertically, I'd have to move 3 units down. So if I recreate those instructions, but starting from the point 0, 0, this time I am brought to the location +3, -3. So the component form of this vector representing this movement would be +3 for the x component and -3 for the y component in brackets, angle brackets. Now notice something interesting about our results here. To find the x component of this vector, what you can do is take the x component of your final position and figure out the difference between the x of the final position and the x of the initial position. The difference between those two is equal to our x component. Likewise, to figure out the y component in our answer, we can take the y of our final position and figure out the difference between that and the y of our initial position. 0 minus 3 would give us this y equals -3. Now, taking that observation and generalizing it to an arbitrary pair of points A and B, we get the following formula. If you want to figure out the components of a vector which stretches from the point A, which I'll represent as x1, y1, to the point B, which I'll represent as x2, y2, all you have to do is this. Take the final x, x2, and find the difference between x2 and x1, the difference in the two x's. And then take the difference of the two y's, final y minus initial y. So as a mnemonic, this is final minus initial. If you want to get an answer with the correct sign, with the plus minuses in the right places, you do have to be careful to make sure that you're subtracting in the correct order. Now, the vector stretching from point A to point B has special representation. It's represented as AB with a long vector arrow stretching from A to B. And order really does matter here. The vector from A to B is different from the vector from B to A. They're going to be the same length, but they will not be in the same direction. The vector from B to A will point in the exact opposite direction. So the vector from A to B is the opposite of the vector from B to A. So order does matter here. For an example showing the differences between these two vectors, let's consider the case where A is equal to 1, 0, and B is equal to 0, 1. So just to make a quick sketch, A is on the positive x-axis and B is on the positive y-axis. So the first thing that they want me to do is find the vector AB with the arrow pointing from A toward B. This is the vector whose initial position, whose tail is located at A, and whose arrowhead is located at B. In part number 2, they ask for the same thing except the order is switched. This time they want the vector to originate at B and terminate at A. This would be the vector stretching from B to A. So I'm expecting that the answers to these two questions will be exact opposites, because the direction of the vector is an exact opposite. Now to find the vector stretching from A to B, I'm going to use the formula final position minus initial position. Now the final position is B in this case, so I'm going to take the final x value of 0 and subtract the initial x value, which is given by the x of the point A, 0 minus 1. To find the y component of the vector, I'm going to take the final y of 1 and subtract the initial y, 0. So this is equal to the vector -1, +1, and this completely matches what we might expect based on our drawing. If I wanted to get from A to B, I would have to go -1 units in the x direction to go to the left, and +1 units in the y direction to go up. Now for the vectors stretching from B to A, the roles of final and initial are swapped. This time the final position are given by the outputs of A, and the initial position are given by the outputs of B. So for this problem we would get the answer +1, -1, which again completely makes sense based on the sketch. To get from B to A, I would have to go to the right by 1 unit and down by 1 unit. Now let's do one final exercise. In this case, we have an object which is moving from the position 3019 to the position 11,7. And let's first find the vector, ideally in components, which represents the movement/displacement of this object, and then subsequently, let's figure out how far the object traveled. So to figure out the vector representing the movement/displacement of this object, I'm going to use the formula that says to find the vector stretching from one point to another, use the formula final minus initial. So I'm going to take the final x-coordinate, which was 11, and subtract the initial x-coordinate, which was 30. I'm going to take the final y-coordinate, which was 7, and subtract the initial y-coordinate, which was 19. And after calculating those two differences, I get the vector -19, -12. Now, how far did the object travel? There are several different ways to answer this question, but one of the more convenient ways is to use the answer that we got in number 1. Because this vector represents the displacement of the object, the magnitude of the vector is equal to the distance traveled. The magnitude of a vector is the number associated with that vector, and for displacement, the number associated with this vector is the distance traveled by the moving object. So I can use the magnitude formula, which says that magnitude squared is equal to -19 squared plus -12 squared. Therefore, the magnitude is equal to the square root of this quantity. The distance traveled, therefore, is equal to, this would be equal to 22.5, approximately. That concludes today's material. Today, we talked about magnitude, direction, and the components of a vector. We found out that the formulas that we gave when working with polar coordinates to convert between polar and Cartesian could basically be recycled and used again in this section. If I had the components of a vector and I wanted to find its magnitude and its direction angle, then I could find the magnitude by taking the square root of the quantity a squared plus b squared. And if I was going to take the direction angle theta, I would either use arctan of y over x or arctan of y over x plus a half rotation, depending on the quadrant of my vector. Likewise, if I had the magnitude and the direction, then I could use the formulas x equals r cos theta and y equals r sine theta to find the components of the vector. We also saw a formula that helped us to find the components of a vector which was stretching from a point A to a point B. And that formula was described as final position minus initial position. Final x minus initial x, final y minus initial y.